Some of those we hit 5 times, spanning 2 years over the 3 different campaigns. So I think this is really the first campaign of its kind that had this kind of aerial coverage, as well as pretty high spatial resolution. So this is kind of a look at what the MethaneAIR data looks like. So this is a map of the Permian Basin from one of our flights in 2021. And this has been aggregated up to a 1 kilometer grid just so that you can see a little bit more of the large scale features that are coming out. So you see kind of big plumes here, and then here, area emissions just kind of mushed together, and you maybe won't see exactly where they're coming from, but you can see kind of the cumulative impact of a lot of emissions coming together. So we're trying to quantify, the basin scale as well as the finer scale. And then here's just some zooming in on some different plumes that we've been able to see. This is a livestock plume from around the Denver Basin. And this is pretty interesting because, the livestock is here, but we could clearly see the plume was coming from this manure pond to the side. This was a really huge pipeline leak that we were able to see. Here's a landfill. You can kind of see different areas of the landfill that are emitting. Gas processing plant. So we're able to see a lot of these plumes. The satellite is going to have about 100 meter by 400 meter resolution. So we're going to see a lot of the bigger plumes, maybe not the very smallest plumes that we saw with MethaneAIR, but quite a lot of plumes as well. So I wanted to kind of take you through our data processing methods to get emissions from a scene like this. So kind of the first step that we do is to identify point sources. So we have a thresholding method that can do this automatically, find a lot of plumes, and we're trying to make it as hands-off as possible. It's not totally human-free yet, but we're trying to get there for the satellite. So we've identified the point sources and quantify the flux from those with a divergence integral method or an IME, integrated mass enhancement method. So, these point sources are obviously really useful on their own, but it also is helpful to the inverse model that we're going to use to get the area sources. Because by treating them separately, we can actually remove them from the geostatistical inverse model and use that GIM to fit only the area sources and not the point sources. So basically the freedom in the GIM can go towards those diffuse emissions rather than those point sources, which are pretty hard to get if you're not getting the wind direction precisely right. So after removing the point sources, we also use stilt to remove the impact of methane from anywhere outside of our study area. So then we can focus in on only methane that was kind of emitted from our domain. So then we finally run that inverse model to calculate the diffuse area emissions. Then we add back in our point emissions to get the total emissions from the scene. So just to give you a little more details on how we do the point source emissions, here's an example of kind of one of the smaller plumes from a landfill in Colorado. So you can see on the left kind of what it looks like in the midst of our scene, and then to the right once we've kind of cropped out the plume itself. So here are kind of 2 different methods that we use for point sources. So on the top here is the IME method. So here we mask out the plume, basically add up the sum of methane within this plume, and knowing the wind speed, you can use that to calculate the emission rate. The other method that we use is the divergence integral. So what we're doing here is basically drawing boxes around the source that basically get bigger by 1 pixel at a time. So I'm only showing a couple example boxes, but we're actually kind of smoothly increasing them through the length of the plume. So I'm showing here the flux calculated basically through this surface as a function of the distance from the source. And I know this looks noisy, but this is actually real variation in the atmosphere. So like, for example, right here, when you have pretty much 0 flux, that corresponds to around here where the methane was just kind of spread out by the eddies. So it kind of piled up here. There's not really any excess here, and then it piled up here again. So we're kind of trading distance for time. So because we're using only an average wind, we're not resolving the eddy winds in the model. But using the average wind, you're going to get high, low, but if you average it out, it actually comes out really nicely to the true flux from that source. And we actually demonstrated this with help from Sahar's group at Stanford with 2 controlled release experiments that were done in 2021 and 2022. And we had, the Stanford group was releasing methane on the ground and we would fly over it. We did about 20 overpasses in 2021, another 20 in 2022. And so this was a blind experiment where we didn't know the control release value until after we submitted our estimates. And so we had really nice agreement both years, particularly well in the second year, which was kind of a cleaner environment. So this 2021 was in the Permian, where there was kind of an unlit flare nearby spewing out methane. There was just a lot of methane coming in from the background. And then 2022 was in Phoenix, Arizona. So it was a lot cleaner of a background, and we did kind of an even better job matching. So it's really nice that we're able to validate these point source methods and show that they're doing a really good job of quantifying the emissions from plumes. Just wanted to show a couple more examples, just so you can kind of see what we can find with these plumes. Here you can see this landfill is emitting from a couple of different sources on the landfill, so we can actually see where people maybe should go to look for those emissions. And it's pretty interesting how they kind of, the wind blows them and they all come together. So we can't quantify these individual emitters here, but we can quantify the sum of them. And then here's kind of a lower emitter, just 380 kilograms per hour. And again, you can see pretty much precisely where it's coming from on the landfill. So here's just a look at some of the statistics from 48 flights that we've analyzed to this point. So our detection limit does depend on wind speed and how clean the scene is. And with this kind of automated detection method that we're using, the limit is around 300 kilograms per hour, but it is a bit higher if the winds are strong. And we are working also to kind of push that detection limit down going forward. And it also can be a little bit lower if we know where to look. So, if we have a list of landfills and we can just go look for a plume at each of those landfills, we can also find a few more plumes than if we do the automated method where we don't know where to look. So yeah, from these 48 flights, we found 94 plumes that were over 2 tons per hour, 16 over 5 tons. And we had this one real outlier, which was a gas processing plant in the Appalachian region. Just to look at how they break down kind of basin by basin. So what I'm showing here is if you add up all the flux from all point sources found in a given flight, and then average those sums by basin. So you can see the Appalachian, this is, a little bit biased high by that one really huge plume that we found. But Appalachian, Haynesville, and Permian definitely stand out as having the most emissions, I think both by flux and an area standpoint, but both by point source and area source standpoint. And just bring it down one more time. So here are our 3 biggest ones: Permian, Appalachian, and Haynesville. And then this is all of the other basins that we covered. So, the other basins, we only found a typical about 4 plumes per flight. So there weren't really that many sources big enough for us to find with our current automated methods. But these 3 basins had quite a lot. You can see Appalachian in particular has a lot in this like 2 tons to 5 tons space, even almost compared to Permian. That could be because Permian probably had lower winds when we were there, so that allowed us to find more of the smaller plumes. Yeah, Haynesville in particular was pretty windy for those 2 flights we were there, so we didn't find a lot of the smaller plumes. But anyway, yeah, we have a lot of big plumes. We have a lot of plumes in general, and we're still working on going through and really attributing all of them so we can kind of break it down by sector and things like that. So one more, we did manage to pick out 40 landfill plumes from 16 flights. There's probably a lot more in there as we go and look in more detail. So these 40 include some that were found with the automated methods and a few that were found just by going like landfill by landfill, but we have a lot more to just take landfill databases and just go looking and see where we can find plumes. So hopefully we're going to find quite a few more landfills, possibly, there's about 300 landfills from our database that we flew over. So we'll see how many of those we can detect a plume in. And what I'm showing on the right here is on the x-axis is the methane emissions, tons of CO2 equivalent that are from the EPA GHGRP database. So this is what the landfills are reporting to the EPA for their emissions based on bottom-up accounting methods. And then on the left is the flux that we calculate from MethaneAIR. So we have a pretty low R squared of 0.27, which is probably not a surprise to anyone who's worked with landfills that these bottom-up methods are not great for giving you a real estimate of what the emissions from a landfill are going to be. So that's been shown before, but I think it's important to emphasize that those bottom-up methods really have a high uncertainty. And I think Carbon Mapper and others who have done a lot of landfill emissions have seen the similar thing. Another example of a landfill that we actually hit 5 times in Commerce City, Colorado. So for one, this can show you just a little bit of how the plumes can look different based on the wind. So here was a really low wind day where the methane kind of blobbed up on top of the landfill, and then windier days, the plumes can get much more spread out. It was kind of interesting that we saw pretty consistent emissions over a few flights and then pretty different emissions over some of the flights as well. And the Carbon Mapper folks who have done a lot more landfills than we have told us that this is pretty consistent with what they see as well. The emissions can really vary quite a lot day to day. It can vary based on the atmospheric pressure, the wind speed, and the season even. So, the 25th to the 26th, we were there 2 days back to back. This was a really low wind day. This was a windier day. So it's possible that the higher wind was kind of sucking more methane out that had kind of built up on the lower wind day. And some other colleagues have shown before that they saw emissions increasing in the fall compared to the summer. So, we don't have a lot of data on this, but it's pretty interesting. I think we're going to be collecting a lot more as the satellite goes up and as we continue flying. So I think we're going to get some interesting insights into these landfill emissions. Okay, so now I want to move on to how we calculate the area emissions. So first, we do this plume finding. We remove the flux from the plumes from the scene. And then the next step is that we remove the impact of methane from outside of the scene. So this work is mainly being done by Josh Ben-Merghi, who I think has presented this series last year. So on the left here, we're showing the observed methane, and then to the right, we've reduced kind of the impact from emitters outside of the area. So you can see this stuff around the edge gets reduced a lot. We reduce a little bit in here. So this is the in situ methane. And so finally, we take our in situ methane minus the point sources, and we're able to calculate posterior emissions. So we're showing the point sources here with the size, proportional to the strength of the emitter. And then we're able to kind of get the area emissions and the total emissions for the scene. So looking at what we saw here in the Permian Basin for this flight in 2021, we saw the heavy tails, the large point sources, being about 7% of the total of the area emissions. All point sources are about 35%, and then the area emissions are 65%. So this is everything that's not a point source. This is the Uinta Basin, also from 2021. We again see that the area emissions are really huge compared to the point source emissions. So the points here only contribute about 12%, and the area 88% of total emissions. So just looking back, this is kind of what we were able to fly over 5 months. Each map is about 100 kilometer by 100 kilometer. MethaneSAT that's going to be going up is going to acquire 30 targets of about 4 times the size each day. So we're going to have a whole lot of data coming down really soon that we're really excited about. I just wanted to also look forward a little bit. This summer in 2024, we have a campaign funded by NSF with the goal of providing a rigorous test of
more
regional area flux models. So we're going to use the aircraft both to validate the satellite, but we're also hoping to do this kind of a benchmark study to kind of give oversampling in space and time such that we can better constrain the total area emissions. So as of now, there's really not a great way to, validate inverse models with any kind of ground truth about the emissions from a large area on this scale. So our plan is to fly MethaneAIR at least twice during the day. So NSF is funding us to fly two flights over an area like this within the day. And we've also reached out to NASA to see if they could fund our other aircraft to fly as well and possibly give up to 4 overpasses within a day. We're going to have EM27 sun spectrometers as well to give kind of the temporal, coverage throughout the entire day. And then we're going to target with MethaneSAT at the same time. So you can see kind of our MethaneSAT target area. So we're hoping to make kind of a movie of the total atmospheric burden of methane as it sets up and evolves over a 2-day period that will kind of allow us to better resolve mass balances than we can get with just one aircraft overpass. And then repeat this at least twice at 2 different sites. And we are looking for any measurement or modeling collaborators who want to be a part of this campaign. So I just wanted to put a little plug there. If you have an inverse model and want to test it on our data, we would love to work with you. And yeah, any other measurements who want to be a part of it would be great too. So just kind of to summarize everything that I've talked about today, MethaneAIR and MethaneSAT are designed to quantify methane from total regional emissions, spatial distribution, and large point sources. So far, our observations from several different basins are showing that area sources account for the majority of total emissions. Point sources are important, but most seem to be majority area sources. So our ongoing work is going to quantify area emissions for the full set of MethaneAIR flights and allow us to compare emissions across basins and over time. And yeah, we're very excited for MethaneSAT to go up in about a month and, fill that observing gap in between the global mappers and the point source satellites that are currently up there. Yeah, please visit methanesat.org if you want to learn anything more about it.
Great. Thank you so much, Marianne. That was really an interesting talk and so exciting to see all the different results that you're getting.